Hello dear students, welcome to YourPedia. Today I am going to discuss one question from power systems that was asked in 2022 ONGC interview for electrical engineers. Okay, that question is one of the good question. In fact, yes, that question is what type of grounding, yes, what type of grounding method is used for a synchronous generator. See, there are several grounding methods like solid grounding, resistance grounding, reactance grounding, Peterson coil grounding. Among these grounding methods, which grounding method is used for synchronous generator? So student must think from stability point of view. See, entire power system will run on the concept of stability. The primary thing is stability. If a power system is unstable, there are many bad consequences. Means there is no power to the country. Okay, power system must be always stable. Yes. So let's discuss what type of grounding is used and why it is. Yeah. What is the acceleration power? Acceleration power PA is equal to the steam input PS minus the electric power output PE. Yes. If you take a generator, any synchronous generator, there will be some mechanical input and electrical output. Under steady state condition means there is no fault, there is no disturbance, there is no change of load. Means the operation of the generator is very smooth. It is running very smoothly without any change of load, no disturbance, no fault, nothing. That is steady state operating condition. I can say acceleration power is equal to PS minus PE. PA is equal to, or I can write like this, PE is equal to PS under steady state. Under steady state. What does it mean by steady state? No disturbance, no fault. Okay, there is no contingency, none of the things are there. PS is equal to PE if there are no disturbances. There are no disturbances in power system network. In power system network, there are no disturbances. Then what is PA? That implies that then yeah, tell me what is PA? PA acceleration power is equal to 0. Means the rotor neither accelerates nor decelerates. The rotor is going to rotate with its constant speed, that is synchronous speed. Neither accelerates nor decelerates. If it is rotating with the constant speed, frequency is constant, obviously the machine is remain connected to grid. It is not going to be disconnected from grid. If the incoming machine frequency is not same as that of grid frequency, that incoming machine will be disconnected. Why? If there is a difference of frequency, dead short circuit will take place. Why? Because there is instantaneous voltage difference between two things, like one is grid, another one is the incoming machine. Circulating currents will flow. Parallel operation is not possible if frequency is not same. Yes, there is a relay called frequency relay which is going to detect the frequency, incoming machine frequency and grid frequency. Yes, if there is a difference and that difference is the difference is continued for a long time, then definitely that machine will be disconnected. There is a small amount of difference, that too for small amount of time, then the machine will not be disconnected. But there is a significant amount of difference of frequency between the incoming machine and grid, and it is going to be there for more time, significant amount of time, then definitely that machine has to be disconnected from grid. Otherwise circulating currents will flow and machine winding will burn. Okay, yeah. Now observe here, acceleration power is equal to 0. Yes, but when fault occurs, for example, I am taking three-phase fault. Three-phase fault means what? A triple L or triple LG fault I am taking occurs. Example I am taking, yes, triple L fault. Yes, triple L fault. For this fault, yes, PE is equal to 0, electric power output equal to 0. When fault occurs, PA is equal to PS. What is PS ma? I'll write here. PA is acceleration power. Acceleration power. Yes. PS is steam input. I am taking thermal station, thermal generating station. Okay, steam input, and PE is electric power output. Electric, yes, power output. This is a PE, right? Now, PA equal to PS. This is positive or negative? Positive. Yes. If acceleration power is positive, rotor will accelerate. Yes, that implies rotor accelerates. Rotor accelerates. See, the present speed is synchronous speed now, and here I'll write that omega equal to omega s, omega r, rotor speed is equal to synchronous speed. Rotor speed is equal to synchronous speed. Let me write here clearly. Omega r is equal to omega s. Now here, now the acceleration power is positive due to fault. Now rotor starts accelerating. You know what happens if it accelerates? Yes, rotor angle changes. Rotor angle keep on increasing. In this case, in this particular case I'm talking. Okay, it accelerates. From equilibrium criteria we know that see, if more is the acceleration, it has to find more deceleration area. If that much amount of deceleration area is not available, then the machine will become, or system will become unstable. Means we want more acceleration or less acceleration? We always want less acceleration. If more is the acceleration, I'll draw that equilibrium criteria diagram also. I'll draw. Yes, I'm drawing here. Observe. Now observe here. All of you very clearly observe. One of the very important concept. This is delta. This is acceleration. This is P, electric power output P. Yes, and this is a P curve. Yes, this is P curve. This is the steam input. This is the steam input. This is a PS, and this is a PE. Now the present operating point is this. The present operating point is this before fault. Means PS and PE both are exactly equal. I'll call this one as initial operating angle delta naught. Initial operating angle delta naught. But whenever a fault occurs, see, this PE completely became 0. This PE completely became 0. Yes, it comes here. It comes here. Yes, and it is accelerates. It is accelerating like this. It is accelerating. When accelerates here, let me write here omega equal to omega s. Here omega is equal to omega s. It is accelerating. Now observe, this is acceleration. Now suppose if the fault got cleared at this point of time. If the fault got cleared at this point of time, yes, fault got cleared. If fault got cleared at that point of time, what is the angle available? So I'll write this one as delta C. Delta C is clearing angle. What is that, ma? Delta C is clearing angle. Okay, it is an angle at which the fault got cleared by the protection system equipment. So if not cleared, what happens? So obviously after some time the power is going to become equal to 0. After that the power tends to become negative. Power tends to become negative means reverse power relay will be there. That relay will disconnect your machine from grid. It is unstable. Yes, we are assuming that here the fault got cleared. This total is acceleration area. Let me mark. This total is acceleration area. This total is acceleration area. This total, yes, this total, and that much deceleration area it looks for that much deceleration area. So that much deceleration area is not available. Yes, this is the deceleration area. This is the deceleration. Yes, this is the deceleration. In fact, see, we have to mark between PS and PE only. Between PS and PE only we have to mark. See, what is the PS? This is this black color line is PS, and what is the PE? From delta naught to delta C, electric power output is 0. Yes, and yes, just something I marked here. Something I marked here. Let me change that. Something I have to change here. Yes. So observe here. This total is the acceleration area. I'll mark it as A suffix ACC. This is acceleration area. This is ACC. AACC. A acceleration. This is A deceleration. A deceleration. If you observe, this particular area is just we are looking at it is not sufficient. Means this is a deceleration. After that again it is entering into acceleration. According to equilibrium criteria for a system to be stable for transient stability, what is the condition? The deceleration area must be equal to acceleration area. Here acceleration area is more. Sir, how you are able to say that acceleration area is more? By looking physically? No. If more is the acceleration, please catch this point well. If more is the acceleration power, PA is more, then more will be the acceleration. If more is the acceleration, it has to search for that much deceleration. See, our curve is fixed. This is 0, this is pi. In this, 90% is went for acceleration, then how much percentage you are left for deceleration? 10% only. Deceleration area is not equal to acceleration area. This machine is unstable. That way you have to tell, not just by looking at the physical area here. Never we look for physical area. We have to count that area. We have to calculate that area. See, means whether a system is stable or not will be decided by what? Acceleration area. Acceleration area is decided by what? Acceleration power. So let me write those note points. Let me write those note points. Yes, that is very important. Note points. Yes. Let me write those note points. Note 1 is, yes, note. System or machine, instead of system, let me write it as machine. Synchronous machine will be stable if deceleration area is equal to acceleration area. Sir, why I can't write acceleration area equal to deceleration area? Which one is depending? Deceleration area. See, if acceleration area is x, I want deceleration area to be x. So which one is coming second time? Means which one is secondary? Deceleration area. Deceleration area must be equal to acceleration area, not acceleration area equal to deceleration area. Why? Because acceleration is happening first, then deceleration, right? Yeah. Then machine will be stable if this is first node. Yeah, acceleration area depends on PA, acceleration power. If more is the acceleration power, more will be the acceleration area. If more is the acceleration area, that much deceleration area is not available. Okay, here people may think for this, sir, if deceleration area is greater than acceleration area, never possibilities. See, why it is never possible? Deceleration is going to depend on the acceleration. Yes, deceleration is going to depend on the acceleration. It may be equal to acceleration or maybe less, but never be more. Okay, so this thing will not exist practically. That's why we won't discuss. Acceleration depends upon acceleration power. Now observe here. If I am taking synchronous generator, yes, this is the synchronous generator. This is the synchronous generator. This is the neutral of the generator. Our question is, which grounding is used? This is the neutral for synchronous generator. Yes. Now we will use resistance grounding. Sir, why I explained this much, I'll tell you. Okay, or not RG, RN I call. Why I explained you this much, I'll tell you now. Now, whenever a fault occurs, suppose if it is a solid grounding, see, suppose if solid grounding is used, solid grounding means what, ma? Neutral resistance is equal to 0. Then what is PA? PA is equal to PS minus P. If resistance grounding is used, PA is equal to PS minus, see, fault current will find a closed path through this neutral resistance, IF. Whenever it is a grounded fault, for a grounded fault, the fault current must take closed path through ground to the neutral of the generator through this resistance. Okay, then what is PA? PA equal to PS minus PE plus 3 times of IF square Rn. Yes, IF square Rn. So whenever during fault, if this is decreasing, but this will be there, so that this PA will decrease, acceleration power will decrease. If there is no this, or I can say like this, better take this PE as 0 during fault, okay. Yeah, now for a short circuit fault, 3-phase short circuit fault, for example, if I take 3-phase short circuit fault current flowing through ground is equal to 0. If I take a LLG fault, line to ground fault, the PE will be very, very small. Neglect it, take it as 0. Here what is PA? PS. Here what is PA? PS minus 3 I fault current square into Rn, means I'll call this one as PA2, this one as PA1. PA2 will be less than PA1. PA2 will be less than PA1. If PA2 is less than PA1, acceleration in this case, if I ground the neutral of the synchronous generator with resistance, will be less. If acceleration is less, that much deceleration area is available, then system will remain stable or the machine will be connected to grid. Yes, if so by keeping this one in mind, by keeping this power system stability in mind, to improve transient stability of the power system, we are going with resistance grounding of synchronous generator. Which grounding is preferred for synchronous generator? Resistance grounding, not solid grounding, not reactance grounding. Why? Because if we are using resistance grounding, then some power will be lost, active power, in fact real power in this resistance. People may claim, sir, that is a disadvantage. No, with respect to stability, that is an advantage. Because of that real power, because of that active power, overall acceleration power will decrease. Why? Because this is acting like a load. Whenever load got decreased, this particular due to fault, whenever load got decreased, this particular resistance is behaving like load, though it is not giving any useful power. Acceleration power is decreasing. Because of its acceleration will decrease. If acceleration decreases, that much deceleration area the system is able to find. Means if acceleration is less, deceleration is also less. Never it cross. Yes, I can show you like this on the figure. Yeah, so before this point or before this angle, let me write this one as yes, before this delta x, the delta x, it will be, yes, before this delta x it will be stable. Okay, see, once if you cross this delta x, there is no possibility for the system to be stable. Before this delta x itself, it has to become stable. Okay, so this is the reason why we are connecting the neutral of the generator, synchronous generator, with resistance to the grounding. Resistance grounding is preferred for synchronous generator. One of the very good concept. Thank you.